Hello, my name is Chu Li, an assistant professor at National Jiao Tong University. The paper I will be presenting today is titled Ghost Codes from Operational 4G Call Systems, IMS Vulnerability, Code DoS Attack, and Countermeasure. For most of the time, many people's phones do not have any incoming call, sign, or ringtone from cellular voice service. It means no one is calling you. Is this always the case? Maybe not. Probably you are under attack. Without discovered vulnerabilities, an attacker may make ghost calls to your phone so that your call resource is occupied, then no one can reach you. Certainly, to launch the attacker just needs your phone number, and during the attack, there are not any signs on your phone. Why may it happen? Different from the former voice services, all the major operations of VO Wi-Fi, which is one 4G voice service over Wi-Fi, are done by the software. So it has larger attack surface. For example, once mobile OS is compromised, the VO Wi-Fi traffic can be intercepted, analyzed, and even fabricated. 4G voice services are supported by a system called IMS. IMS is used to support various multimedia services in the cellular network. For the voice services, the call operations relies on SIP for call signaling and RTP for voice delivery. There are two kinds of 4G voice services. One is VoLTE, where UE connects to the IMS system through LTE base station. The other is VO Wi-Fi, voice over Wi-Fi. Its connection goes through Wi-Fi AP and the internet. Here you can see VO Wi-Fi traffic needs to traverse the public domain, so it requires higher level security protection. To protect the VO Wi-Fi traffic, an IPsec tunnel is built between UE's Wi-Fi interface and the security gateway in the 4G core. The other IPsec session for specific application VO Wi-Fi here is built between the UE's virtual interface and the IM system with the transport mode. However, they can be hacked. VO Wi-Fi synchronization can be hijacked. It allows an attacker to manipulate IMS call service operation. If IMS has any vulnerability which were hidden by the former voice solutions, they can be exposed to attackers now. Overall, we discovered three security vulnerabilities. VO Wi-Fi synchronization can be hijacked due to the first vulnerability, no application level data origin authentication. Based on the session hijacking, the attacker can interact with IMS on a per message basis. We then discovered that the second vulnerability, concurrent call attempts are allowed, and the third vulnerability that callee may get stuck in the call state machine. These vulnerabilities have been validated in two Asia and two US carriers using 15 phone models with 7 phone brands. Currently, the data origin authentication is device level. So, access of the synchronization is not restricted to only IMS application. When mobile OS is compromised, a malicious application can intercept and fabricate the IPsec session packet. Moreover, when the IMS application relies on the system to carry out the IPsec transport, a malicious application can fetch related security parameters from the system and fabricate valid IPsec packets. One thing to note is that any packets are correctly encapsulated by the IPsec transport. They can be sent to the core network through the IPsec tunnel by the system when the packets are sent to the Wi-Fi interface with the correct session information. To fabricate valid SIP and IPsec messages, there are two major steps. First, we need to have valid SIP information. For this part, we can get SIP information by observing benign SIP messages. For example, SIP server address, proxy address, front tag, and the call ID. The second step is to add IPsec ESP integrity protection to each packet. Here we apply the default ESP pending algorithm, keep track of the IPsec secret number, and finally generate authentication data using the fetch algorithm and the keys from the system. We conduct an experiment to validate whether the session can be successfully hijacked. Here is a trace showing that a forged SIP invite can successfully ring the callee. This is tested with the fake session name to show that this message is indeed fabricated by the malicious application. Then here we can see that the coder can get the ring packet sent from the callee. So it shows that the session can be indeed hijacked by the malicious application. It can be considered as a design defect of the IPsec transport protection because it is only device level, but not application level. It may be good for conventional voice solutions protected by the hardware modem, but it would be vulnerable for the VO Wi-Fi service. Malicious application can easily break it. And then we further find an operation flow from two carriers. That is, the mandatory IPsec transport protection is even missing. Then these two carrier networks would be more vulnerable because the session hijacking can be easily done without generating IPsec security payload. With the IPsec session hijacking, we can manipulate IMS call service operation on a per message basis. The call setup procedure is similar to that of conventional VoIP services. It is initiated from an invite message. After a message handshake, the callee starts to ring while replying a ring message. We got two questions. First, can we generate multiple invite messages concurrently to make concurrent call attempts? Second, can we get the callee stuck somewhere in the call state machine? For the first question, actually, making concurrent call attempts is prohibited by the system GUI and the call API. Simply, only one call attempt is permitted to be made at a time. But is this really the case for the IMS call? If not, the attacker can make multiple calls arbitrarily and concurrently based on the hijack sessions by sending out multiple invite messages simultaneously, and also maintain a session state associated with each invite. We conduct an experiment to validate the answer. We develop an application which makes two concurrent calls to two callees. Here is a trace created at the coder where our application is. The messages marked with red rectangles belong to one call session. The other message with blue rectangles are owned by the other call sessions. We can observe that the calls are successfully made to two different phone numbers. So the second vulnerability is no prohibition of concurrent call attempts. It can be considered as an operational flaw. It could be inherent from the support of concurrent call sessions in a conference call. And call attempts are considered as call sessions, so concurrent call attempts are allowed. It was hidden by the device system GUI and API. However, when the attacker can hijack the synchronization, this flaw can be exposed. So IMS needs to differentiate call attempts from established call sessions and then set different limits on them. For the second question, can the callee get stuck somewhere? Security issues are usually expected from new methods. So we try to examine the call procedure to see what's difference compared with the conventional VoIP call procedure. We observe that there is a new control message which is called preg. This is used for the reliability of provisional responses such as session progress. Okay, so the reason we have preg in a call procedure is that VO Wi-Fi needs to offer carrier-grade call quality. The establishment of an IMS call may fail in the absence of sufficient resource, and meanwhile the callee may have been alerted. That's it. Without sufficient resource, an invalid call may cause a phone to ring. This is not acceptable in cellular voice services. PREG is last introduced for this resource reservation confirmation. It is sent by the caller after receiving the session progress. What if PREG is not sent? Does the callee keep waiting? The answer is yes. The callee can get stuck in this proceeding state, which waits for the PREG. Without receiving PREG, the callee retransmits session progress with an exponential backoff timer. During this unsuccessful call setup, the callee is not able to accept another incoming call. So the third vulnerability is abusing reliability of provisional responses to calls denial of service. We conduct an experiment to measure the call denial of service duration caused by a call attempt. An attacker initiates a call attempt without replying PREG. When receiving session progress, the attacker asks a tester to keep initiating call attempts to the victim. Then the call DoS duration can be estimated when the first call attempt from tester is accepted. Based on the results we observed, for carrier US1, the DoS time is larger than or equal to 14.5 seconds. For carrier AS1, the DoS time is larger than or equal to 32.4 seconds. It depends on the timeout values of the retransmission in different carriers. It is reasonable to enable the reliability mechanism because cellular resource is costly compared with internet, and the cellular call service must be carrier grade. It can be considered as the design defect from standard because the standard does not prevent negative impact from the reliability mechanism. Apparently, when this new feature was adopted, its security impact was not carefully reviewed. Based on the above three vulnerabilities, two attacks can be developed. The first attack is stealthy call DoS attack. Victims cannot receive any incoming calls or make any outgoing calls during the attack. Moreover, the victims are not aware of this attack. The second attack is attacker can create large-scale concurrent call attempts to make many missed calls for social engineering attacks. For both attacks, only phone number is required from the victims. So here we focus on the first attack, stealthy call DoS attack. The DoS attack caused by a call attempt can be considered as a building block. The attacker can keep generating call attempts to make victims suffer from long-term DoS attack. In this attack model, the attacker just needs commodity smartphone and the victim's phone number. But the victim has to be using 4G call services. For the impact on the victims, the attack can cause up to 99% DoS time without user awareness in operational 4G networks. However, call DoS attack may fail. There is a non-DoS window between the cancel sent by the IMS and the invite. A normal invite may sneak into this non-DoS window, so this next DoS phase may fail. We need to shorten the non-DoS window by sending cancel actively from the attacker instead of IMS. We further find that there is a queuing period for invite. When the normal invite arrives before the cancel within that period, that invite is still accepted. So we need to send the invite of the next DoS phase right before the cancel to reduce the non-DoS window. To reduce the failure probability, we adaptively adjust the standing time of the invite to approach the minimum of the non-DoS window. So we propose an adaptive multi-layer DoS attack. We use two-level call attempts, which are two concurrent invites based on vulnerability 2. The first invite is called dynamic invite. We adaptively adjust the standing time of this dynamic invite to minimize the non-DoS window. Since this invite may fail, to ensure the DoS can continue to succeed, so we have the second invite, which is called last line invite. This is used to ensure the DoS can succeed. So we pick a sending time, which is always successful for this invite. However, the DoS attack can work for only idle 4G users with the same carrier as the attacker. When target users temporarily hand over to 3G or with another different carrier, the attacker fails. The next question is, can we detect attackable phones remotely and silently? The answer is yes. We can infer remote phone status based on initial SIP messages. The phone status includes call state, idle, calling, and talking, voice technologies, 3G, via Wi-Fi, and VoLTE, and the inter-carrier or intra-carrier. The attackable phones have to be idle with VoLTE or via Wi-Fi in the same carrier as the attacker. The major idea here is that the SIP message content, flow, and the interval may vary with different phone statuses, because their call attempts may be processed by different network entities and procedures. Based on the initial SIP messages, each silent attack call can also detect the victim's phone status. It can be considered as a vulnerability of the 4G network architecture, remote call information leakage. We collect and examine SIP messages by making call attempts to various callees. There is too much information in the SIP messages, and moreover, its rules may vary with carriers, so we apply SBN into the category classification, and we collect SIP traces from more than 5,000 call attempts. Totally, there are 18 categories, but since we are not able to differentiate all of them, so we group them into 4 categories. They are 3G ready, calling, via Wi-Fi VoLTE ready, inter-carrier. Ready includes both idle and the talking states because we are not able to differentiate them, but it is fine for our attack. So we use 14 features to examine which kind of features can be used to differentiate different categories for each carrier. So we consider SIP message content. Then we also consider the interval between 2 messages. For example, the try-in PR interval. This is the interval between try-in and the session progress messages. We observe that the interval varies with different call technology and state. For the classification result for carrier AS1, these 4 categories can be differentiated based on the deterministic SIP message content. So the accuracy is 100% for all the 4 categories. For US1, they are differentiated partially based on non-deterministic message intervals, so they are not completely differentiated. They have small errors, but we can still use multiple tries to reduce the error probability to be below the threshold. To evaluate the call DoS durations, we consider 3 attack modes. One is adaptive, the second is static, the third is multi-victim, which is the attacker attack multiple victims simultaneously with the static attack. Static attack means we use only a single call attempt. So the adaptive one can achieve up to 99% DoS time. Concurrent call attempts to multiple victims may cause some delays of SIP delivery, so the DoS times are reduced for multiple victim cases. The detections incurs only small overhead. It can reduce DoS time up to only 1.6%. Then we propose solutions for each vulnerability. For the first vulnerability, we propose application-level data origin authentication. The application should serve as one entity of the IPsec Transport Security Association. For the second vulnerability, we propose call limits decoupling. The third, we propose delay call binding. We should bind the call to the earliest one, which retains prereq instead of invite. Their effectiveness have been validated on our prototype using open IMS core. So in this work, we have shown that via Wi-Fi synchronization can be hijacked to expose IMS vulnerabilities. The vulnerabilities call for immediate attention from different entities. And moreover, we have been working with GSMA to address the vulnerabilities. Thanks for your attention.